Everyone, I would like to start today's lecture with an R format instruction, which is called set less than, or SLT. So set less than is an R format instruction that takes three registers, RS or RT, and what it does is if the register file of RS is less than the register file of RT, then we have register file of RD is equal 1, else register file of RD will be equal to 0. So this can come pretty handy when doing comparisons. For example, if I want to say write a program that places in memory location 0x200 the value 5 if the value of R, the register S0 is less than, let's say, 70. So the way I write this program is as follows. First, I need to set up my addresses, so I'm gonna place add I $s1 the value $0, and we're gonna have 70 in decimal. Then I would like to set up the address $s2 0x200. Then in this case I would need to compare the value that it's in S0 to 70. So here I say set less than $t0. So I want to say that S0 is less than 70, which is found here. It's in S1. So now I have two choices. I need to check if T0 is 1 or T0 is 0. So if it's equal to 0, this means it's not less. So I'm gonna say branch not equal T0 0, and I'm gonna go to less than 70. So this is my label. I can name whatever label I want. Here I'm gonna say, okay, if it's not, I'm gonna just close the program, exit, jump to exit. So this is just stops the program and will be in an infinite loop. Otherwise, it will jump to less 70. And here I know that the value is actually less than 70. So I want to place 5 in the memory location 0x200. So here I'm gonna say add I T1 0 5. Then I'm gonna store this value in location 200, which will be in S2, and then I can go jump to exit, and this will finalize the problem. So this is a small example about set less than. Of course, I can have an I format version, which takes set less than or RT or RS and an immediate. So I could change this, instead of placing this 70 in a register, I could just say set less than $t0 $s0, set less than immediate, apologize, S0 comma 70, and this will be in place of the set less than and the add I. This will save me actually placing values in a register and using set less than. The second instruction that will help us in loops is shift left logical, or shifting instructions. So in shifting instructions, what I do is I actually, let me take these papers out. So in shifting instructions, I have shift left logical, set less than. So now I would like to discuss another instruction, which is the shift instruction. Of course, we're going to be talking about the logical shift instruction, which is logical shifts, which doesn't care about the sign bit. So if I have a number like 4, 0, 0, 0, 1, 0, 0, of course we have many bits. If I want to shift them one time to the left, it's going to call it shift left logical. Okay. Shifting once to the left will lead to something like this. So this is 4, now it's going to be 8. So what I did is actually I shifted 4 by 1, 0. I can do many shifts, so I can give any number of shifts. Now the MIPS instruction for shifting is called, in this case shift left logical, is SLL. It's an R format instruction, and it takes RD and RT and shamped. You remember shamped is the field just before the function. This is shamped, shift amount. As you notice also, there's no RS. RS is set to 0 by default. So let's take an example. Let's say I want to shift. Let's do this example. So now we're gonna do something like add I $t0 $0 4, and then I'm gonna do something like shift left logical. I'm gonna place it in T1. We're gonna shift T0 by just one place. So if I the value of course of T1 will now be 8. So let's say I told you write the binary representation of this instruction here. So of course it's an R format instruction. The function over opcode over function is going to be 0 0. So both of them are zeros. So for the opcode, I'm gonna just place 6 zeros since the opcode is 6 bits. RS, as we said, it is also set to 0. 3, 4, 5. They are 5 bits. Here we have TZ. So here we have RS. Now RT. RT is this guy here. RT will be 8. From the register file, I know this. And then RD will be 9, which is T1. Also, this is 5 bits, 5 bit. The shift amount will be just 1. So these are 1, 2, 3, 4, and then 1. And then here we have the function is also 0, so I'm going to place 6 zeros. This is 5 and this is 6. So this shamped will go here. Okay, so shift left logical is just shifting zeros and moving all the bits to the left, Of course, we have another instruction which is called shift right logical, and so the same thing takes the RD, the RT, and the shamt. And of course, instead of shifting left, it shifts right. So if I want to take to give an example that kind of groups most of the ideas together, I'm gonna go ahead and write this code. So write a MIPS assembly code for the below C-like code. So let's say I want to fill an array with 1, 2, 3, 4, 5, 6, 7, 8 for us. So let's say I have for I equal 0, I less than or equal than 10, I plus plus. So I want to do something like A of I is equal I. So pretty simple code. So let's see how we can write this in MIPS assembly code. So first I need to initialize the variables. First I have 10 elements, so let's say I'm gonna place add I or T0 or 0, and then I'm gonna place 10. This is the size of the array. Okay, the comment. Now let's say the address is in location 0x200. So let me set up the address. So this is address of A, the array. Now for this I need now to introduce the variable I. So I'm gonna say add I or T1 or 0, 0. So this is I equals 0. Now here I set up my variables. So the first step is just setting up your variables. Now I want to create this loop. So first let us do loop. And now the first step is setting up the address. So I need to have A of 0 equal 0. So this is in C. In MIPS is gonna be the same. So let's do another one. A of 1 will be equal to 1. However, this is in C. In MIPS, this will translate to A of 4 equal 1, because as we know that it's byte addressable memory, and the way the index increase is by a multiple of 4. So first I'm gonna do a shifting instruction. This will become apparent later why I did this. Shift left logical. So I'm gonna say door T2, and where is my index? This is T2 door T1, comma 2. So this is just saying that I having I times 4 inside of T2, and then I'm gonna add this value to S0. So door S0 door 0 door T2. So what I did here is just I'm saying that, excuse me, S0 door S0 is equal door S0 plus T2. So if I have 200, 0x200, then I'm gonna add at the first iteration 0. Okay, so now I can store in the address the value of I, which is set to 0. So store door T1 0 door S0. So now I'm saying in this case that the memory of door S0 plus door T0 is equal 0 because the first iteration T1 was just 0. Now I will increase my index with 1, and then when I reach 10 I need to exit the loop, right? So here after T1 is equal 10, this will break. So branch, I'm gonna use the branching instruction. Branch when they are not equal for door T1 door T0 loop. So in this case here I'm doing I is equal I plus 1. Here I'm saying if door T1 equal door T0, exit. So here is exit. So let's do another trace on this program. So first we started with 0, I equal 0. We multiplied by 4, it's gonna stay 0. We're gonna add it to our address, it's 200, so it's still pointing to 200. And then I'm gonna store T1, which is 0 in this case. The next iteration I'm gonna do it in another color. So the next iteration here we have T1 now is equal to 0 plus 1 equal 1. So here we'll have, instead of 0 times 4 is going to be 1 times 4 equal 4. And now I'm going to add it to the address, is going to be 0x200 plus 4. So now I'm pointing to address 0x204. I'm going to store the value of T1. Now it's going to be 1. I'm going to add again, and now instead of 1 I'm going to go ahead with 2 and continue doing this until I reach the end of the loop, which is 10 times. So in this array is going to have 0, 1, 2, 3 until I reach the value 9. The value 10 will not be executed because I will have exceeded the 10 iterations I have. So this is also 0x200 plus 0, and then I'm doing something like this, plus 4 and so forth, 0x200 plus 12. So this is a simple problem that is incrementing with respect to 200 by 0, 4, 8 and 12. Now so this is how you can do a loop and arrays at the same time. So for the next problem I'm gonna go into machine language with some instructions for in MIPS. So now let's concentrate on working on machine language and translating from instruction to their binary representation. So assume I have in the program memory, this is the program memory, and I have these instructions. They start at address 0x0ab04. Of course this address is 32 bits, but I'm not gonna write all the zeros. Now it is byte addressable, same way as the data memory. So of course the next instruction will be at 0x0ab08. Then I have 0x0ab0c, 0ab10, and then 0x0ab14, and 0x losing the b ab18. So these are the addresses in program memory. An increment of 4, since it is byte addressable. Now let's say I want to translate this instruction, this, and this, since we already saw shift left logical and how it translates to binary. So now I'm gonna start with add $S0 $S0 $T2. So first I need to check what's the opcode and function. For this, I have the MIPS reference sheet. As you see, I underlined the add. It has a opcode over function 0 and 20 hex. 0 for the opcode, 20 hex for the function. I also need to remember how the R format looks like. So it's also available for me here. I can see the first 6 bits are the opcode, then RS, RT, RD, shamt, and function. So let us follow this reference sheet to do the transformation. Furthermore, I have here the registers and where they are located at. So I can see I have S0 is at 16, and T2 is going to be 8, 9, 10. So it's at 10 because it's from 8 to 15, T0 to T7. So let us do this. So the first is the opcode. It's going to be zeros. 1, 2, 3, 4, 5, 6 zeros. Then I have the RS. This is opcode. Then I have RS. RS is going to be 16. So 1, 2. So this is RS. RT is going to be T2, which is 10. So it's going to be 0, 1, 0, 1, 0. We notice that these are 5-bit. 1, 2, 3, 4, 5. And then we have the RD. It's also going to be 16. Then we have, I'm going to continue here, the shamt, which is 5 bits of zeros. And then the function, which is 20 hex, is going to be, this is 2, and we have 4 zeros. So the instruction, I'm going to write it again. It's going to be 1, 2, 3, 4, 5, 6 zeros, 1, 0, 0. This is the RS, RT, RD, and then we continue with the shamt and then with the function. If I want to take the binary, the hexadecimal representation of this instruction, it's going to be 0, 2, then it's going to be 0, this will be 8, this will be A and 0, then I take those 2 and it's going to be 2 and 0. So the binary representation of, or the hexadecimal representation is 20A8020, which is the representation of add instruction. Now for an I format instruction, we're gonna translate add I into binary. So first I'm gonna take a look at the I format instruction here. We can see it has an opcode, RS, RT, and an immediate. It's a 16-bit immediate. The add I has a opcode of 8 hex. It does not have, of course, a function because it's an I format. So let's start with this. So we start with the 8 in hex for the opcode. And then $T1, we notice that $T1 is 9. So, and then we have RS is 9, RT is also 9. And then we have the 16-bit immediate. So we're gonna have 15 zeros and 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for this, if I want to write it in hex, this will be 1, 0, 0, and 0. So now I will take the first 4 bits. It's gonna be 9, and then from here we'll take another 4 bits. It's gonna be 2, another 4 bits. It's gonna be 1, and here we're gonna have 2. So the hexadecimal representation is 0, 2, 1, 2, 9, 2, 3, 1. So this is add I in binary. Now what about branch not equal? For the branch not equal, $T1, $T0 loop. So we can use the formula, which is PC target is equal PC of the branch plus 4, because we fetch the next instruction, plus 4n. So this is going to be PC target is where I'm supposed to go, which is 0x 0ab04 is equal PC branch, which is this guy, 0x 0ab10 plus 4n. Now if I want to do the subtraction, plus 4, we missed here the plus 4, so it's gonna be 0x 0ab04 minus 0x 0ab14 is equal to 4n. So now what I have is 0x 0 minus 1 4 is equal to 4n. Now if I want to divide this by 4, I just shifted the right two places, or I can do just divided. If I cannot just divide it by 2, it's not 7 actually, so we cannot just do a simple division like this. So if I want to do it manually, so this is 1 0 0 and this is 1, and we have zeros, this is minus, so I can shift it twice to the left, to the right, sorry. And it's going to be 1 0 1 and all zeros. So the actual number is minus 0x 005. I can do 2's complement now. For the 2's complement, I can do it. So we'll have 0 1 0 1 1 1 1, and then we add a 1 to have the 2's complement. So the final number is 1 1 0 and all ones. So n is 16 bits. It's going to be 0x f f and another f, and this is b. Now to write this all in I format, we start with the add I instruction, which is it's going to be with the branch not equal instruction. We go ahead and check the branch on not equal. It has 5 hex. So with 5 hex, so this is BNE, it's going to be 0 0 0 1 0 1 1 0 1 0, and we will have RS, which is T0, which is equal to 8, and then we have RT, which is equal to 9, and then we have the 16-bit immediate, which is going to be 12 ones, and a B. Now if I want to write this in hexadecimal, this is going to be B F F F, and we take this, it's going to be 9 0 5 1. So the hexadecimal representation will be 1509 F F F B. Now the last instruction I'm gonna do is the jump instruction, and this jump instruction uses pseudocode. So let's write this: jump exit, and jump exit, it has 6-bit opcode and 26 bits immediate. So if I take a look and search for the jump instruction, it has 2 hex. So 2 hex is like this. We have this to hex, and now we need to calculate the 26 bits. So jump use pseudo address. So the first thing I'm gonna do, I'm gonna check the target. It's 0AB18. Of course, this is going to be 32 bits. So I'm gonna write this in 32-bit representation. So it's gonna take a while. So I'm gonna start from here. This is 8. This is 1. And then we have B. And then A. So this is 16 bits. Now we have to do another 16 bits. So this is the 32-bit representation of exit address, which is here. Now, in order to transform this to the pseudo address, I'm gonna take the last 2 bits and take them out, and the first 4 bits, which is the 4 most significant bits. As we said, this is very easy to know because we know that all instructions have 2 zeros at the end because they are multiples of 4. And we don't expect the jump to be that big. So we don't expect it to be that big, so we can eliminate the first 4 bits and we are left with 26 bits. So now what the address is as follows. We just write those bits down. So they are 1, 2, 3, 4, 1, 2, 3, 4, and now 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, and 1, 0. So now if I want to change this to hexadecimal, I will just have to write it again, because this is here is it's too small. So 0, 0. And then have 4 zeros, another 4 zeros, 4 zeros, 1 0, and 1 0. So I start from the right, and I go like this. This will be 6. Those 2 zeros with this 2 1 will be C. This will be A. This will be 2. And then 0, another 0, 1, 0. So the hexadecimal representation will be 1002AC6. If I know this is a jump instruction, then I can also recreate this address. So I take the last 26 bits, which was this, add the PC, which are the 4 bits, which are all zeros, and add 2 bits, and I will recreate the address again. So we always take out the least 2 significant bits and the 4 most significant bits, and we will have, this is 26 bits. 26 plus 6 equals 32. So we have the 32-bit address. And this concludes this lecture